So welcome back for the post-lunch session. So Professor Subhendra Mohanty is going to talk about some basic stuff about GW.
Okay. So in this workshop, we are going to discuss the field theory aspect of gravitational waves, for instance, memory theorems, memory signal and soft graviton theorems, also gravitational waves generated from phase transitions and so on. So this kind of treatment of gravitational waves requires them to be treated as quantum fields or in classical fields, whereas the standard way is to calculate this using Einstein's gravity. So metric is a geometric thing, not a field. So the purpose of this lecture is to just bridge the gap between these two languages so that so this is for those people who are following the standard calculations of predicting. I mean, you take a source and you find out what's the gravitational wave signal from that source using classical gravity GR. And the same thing, if you want to do it in a quantum language, like treat it like a Feynman diagram and calculate your gravitational wave signal, then this is the language you have to follow. So this is a sort of bridge lectures between these two formulations, and this is meant for students, very elementary. Okay, so you have seen that gravitational waves are that when you take this metric and you take the background, let's say Minkowski space, or in terms of inflation, this is your de Sitter space, so some background plus the perturbations. And this is your gravitational waves, the perturbations of your metric around a flat background. Now, this is done when this H is just the strain, for instance, that if you have two test particles, like in LIGO, and a gravitational wave passes through them, then the strain, the change in the length or distance between the two test particles divided by the length, that is the strain, that is proportional to this guy. So this is your geometric, this is your dimensionless quantity, and that's your gravitational wave. So that's the operation meaning of gravitational waves when you measure it in experiments like LIGO and so on. But when you do field theory, then you take this metric and perturb it with a dimensional constant, which is kappa, and kappa is 32 pi g square root. And the reason we do that is that here this is dimensionless, but if you want to treat this as a bosonic field, spin to bosonic field, then this has to have dimension 1 of this should have a mass dimension 1. Okay. So we multiply with this this particular constant to give it a mass dimension 1. And why that particular constant? So to motivate that, let me start with the Einstein-Hilbert action, which is so this is the action for gravity and matter. Okay. And the matter couples through gravity to gravity just by the metric. So you have to write the metric, the matter Lagrangian, in a covariant way. And that tells you the entire coupling of matter with gravity. Okay. Now, I expand this. Okay. So if I start with this, okay, I start with this expansion, what I get is that, and I calculate my Ricci scalar. So I hope you know how to calculate a Ricci scalar from the metric. So it's a second derivative of the metric, and what we do is we substitute it here, this metric here, and keep terms the leading order in H. So in this case, the leading order in H will be quadratic in H. Okay. So this will be, so I'll write down the entire expression that you will get, box. Okay. So this is coming out from this R, this thing inside. And what you see is that, okay, so first let me choose a gauge. So what does a gauge mean? Let me explain what a gauge means. So in GR, the symmetry is the general coordinate transformation. So this x mu goes to x mu prime, which is x mu plus an arbitrary 4 vector, which is a function of x. So it's a local symmetry. Okay. So this is the symmetry of the, and under this, your metric transforms as, sorry, so G prime, X prime will be so if my indices are put correctly, this is the way second rank tensor transforms. Now you take this linearized metric. Huh? Oh, sorry. Well, both should be true, no? If I take, huh? Okay, if this is, yeah, you're right. So I could do this then. Yeah, so this should be X prime. Yeah, thank you. Yeah, so now if I take this and I write this transformation, okay, and I want to find out what is the transformation on my H mu nu by substituting here, then that would turn out to be H mu nu goes to okay. So I have an arbitrariness in defining my H mu nu. Just like in electromagnetism, you have a gauge transformation. This is the gauge transformation for gravity. Okay. And now, using this freedom to define my H mu nu, what I can do is I can pick a gauge to make this look simpler. Okay. And that is called the Didonder gauge. So that's one gauge choice. So we choose what's called the Didonder gauge. And in that gauge, so the gauge is del mu So this is the gauge choice you make. Okay. So what we have to do is choose a xi such that my h mu nu satisfies this condition. Okay. And then when I put this thing over there, okay, use this condition there, and this is also written as del mu h. So h is h alpha alpha. So once you have this h mu nu, the raising and lowering is done by eta mu nu. Okay. And with this gauge choice, then my action becomes okay. And in all this, this box operator is the normal flat space box operator. Although in curved space, you should put in the connections when you write the D'Alembert. But we are taking the leading order in h mu nu, which are already there. So that's why the box operator becomes the normal flat space D'Alembert. Okay. So this looks like the kinetic term. Okay, you have this, but to make it look a dimensionless form, what we'll do is we'll take this h mu nu to this kappa h mu nu. When you do that, plus of course you have matter. So when you do that, okay, the kappa square is just the denominator. And so basically, if you had expanded in this way, okay, the kappa square would have come in the numerator, which would have cancelled that denominator. So then you would have basically Einstein. Okay, so this thing is no longer there. Plus S. So that is the rationale for choosing that kappa, that in the Einstein-Hilbert action, okay, the h mu nu is a dimension 1 field, and it has a non-kinetic term, which is a canonical kinetic term. Okay. So okay, so now we just define this guy as h bar mu nu, which is h mu nu minus half. And so this Einstein-Hilbert action is h mu nu box h bar mu nu. Okay, so there is this mixing of the two, but we'll disentangle them, plus your, sorry, the matter one. Okay, so now to what we have to do is that we want to find out equation of motion, so we want to write the Lagrangian equation of motion, the Euler's equations from this. So we have to vary this with respect to this h mu nu. Okay. And to vary this with respect to h mu nu, what we do is we expand the matter Lagrangian around the g mu nu to the linear order in h mu nu. Okay, because I say you have taken the g mu nu, the matter Lagrangian. So an example of matter Lagrangian would be like g mu nu something of that kind. And we should, this is an example. So we have to write these G mu nu's in terms of linearize, in terms of H mu nu, and then when we have both sides written in terms of H mu nu, we can vary it with respect to H mu nu and find out the Euler equations. Okay. So let me, still have a lot of space. So delta S, which is, I want to expand this Sm around eta to the first order in H mu nu. Okay. Huh? What did you say? Thank you. M square phi square. Yeah. Okay. So this is so this is my first order term in if I expand this around the flat space, okay, then I can write it like that and then use this. So this term comes from varying the square root of g, keeping Lm constant, then you keep this and vary Lm. So there are two terms and we use these relations which can derive, but and you can write delta Sm as okay. And then the first order, as I said, now we have to take this first order correction as kappa h mu nu. Okay. Right, so far. And this thing inside, what I have written inside, is just the T mu nu. So this is the definition of your stress tensor. This is for any action. So if I take this, okay, then this thing becomes basically the minus sign. No, this becomes a plus sign. Okay. So, and this should be this times delta h mu nu, which is basically kappa. What? Root? Root minus g is now 1 because you are taking it at eta mu nu. I think that gives you a minus sign. That root, so then the sign changed to plus 1. Okay. So now you take this part and your this part, the Hilbert part, and vary with respect to this h mu nu. Okay, and I think I made a mistake here. This should have been there should be in a box here. Sorry, h mu nu box of this. That is my so take the gravity part and the matter part, and vary that has a h mu nu also, and vary with respect to h mu nu. What you get is basically this equation of motion. So varying with respect to h mu nu. And this guy varying with respect to this h mu nu will give you kappa times t mu nu with a plus sign. So you take it to the right hand side, that becomes minus half kappa t mu nu. Okay. And so this is my basic, the equation I get. And now you can see that in the action, okay, the interaction term between the graviton and the matter is kappa. Okay, so this is kappa t mu nu, h mu nu, or you can write it the other way if you want. So this is a important result. And now, since I did not write the form of t mu nu, I just said that varying the action with respect to metric gives me my t mu nu. That's the definition of t mu nu. That means this is a universal coupling. That everything here, this is a universal coupling, and for any type of matter, you write its t mu nu, and that's the, and that kappa is that's square root of 32 pi g. Okay, all right. So now I'll write the equation of motion, which is I define something called and so my basic equation of motion is so I can okay. So this kappa h mu nu type of expansion was important if I want to find out what is the coupling between these guys. Okay, so this is useful if I want to treat like this as, let's say, a t mu nu, h mu nu, and this vertex would be kappa by 2. So this would be a gravitational radiation from, let's say, a binary or a star going around another star, so there is some acceleration. So there is this binary star, and if you write the t mu nu for it and calculate its Bremsstrahlung using the quantum method, you will get the same answer as Einstein, the standard calculation. Okay. And here, the fact that you should get the same answer is not surprising, even though you are using a different language, because as we know, when there are no loops, okay, the tree level, these type of diagrams, the quantum method will give you the same thing as a classical result. Yeah. I'll come to that. Wait. Yes. No, not yet. It's not gravitational wave yet, because what happens is this is just the gravitational perturbation. So supposing this is a real particle, then it's a gravitational wave. But if you have a diagram like that, okay, then you can have H00 is also there, which gives you the Newtonian potential. Okay, so when it's a free particle, then only 2 degrees of freedom are there. But if there are, it's not a free particle, it's a virtual particle, this one, then there are more degrees of freedom. So I'll explain that. Okay. And I think here I should point out one more thing. Oh, I've reached the thing. Okay, just so please remember, so this is the result which I need to do this quantum treatment. But just to make connection with the standard story, I'll so supposing right now, and in the rest of the lecture, I want to calculate these waveforms. Okay. Then what is the equation? You can see that the correct equation is okay. Yeah. This is the correct equation from Einstein's gravity. Okay. How do you get this? Basically, you start with this g mu nu is equal to this is Einstein's equation. Expand this to linear order in H, use the same gauge conditions, and you will get this. Now you'll see that there is a discrepancy between this coupling and that coupling. Okay. There is a square root of g there, whereas this is g here. And that is due to the fact that now this H is a dimensionless number. You can see, check the dimension on both sides. This is a dimensionless number, object, whereas there it's a dimension 1 field. So as I said, the translation between the two is that you start with the equation on that side of the board and make this transformation that divide by a kappa, because that was derived by taking the kappa expansion. Okay. And if you want the expansion, the standard GW expansion, then you take that result and divide by kappa and you will get this. Okay. So you can check that. So I'll go. So I just wanted to make a connection between the two languages. Now, why did I go through that in a more complicated way? Because if you look at this equation and you try to find out what is the coupling between graviton and matter, you will think that the graviton matter coupling will come from an effective Lagrangian which has a T mu nu times H mu nu with this 16 pi g. But it's actually square root of 16 pi g, or square root of 32 pi g. So the expansion that I did is the correct way if you are looking for the correct vertex between the graviton and matter. Whereas if you are trying to find out the equation of motion, the classical gravity, that is the gravity as a strain, then you start with Einstein's equation, linearize it and get this, and then put this as a source and find out what is the wave. Okay. So these are two different things you are doing when you do this. Okay. So if there is a confusion, you can ask me again tomorrow. Okay. So now I'll answer. So for the rest of today's lecture, what I will do is the following. So I have to first address the degrees of freedom of the graviton, like you were asking, that's important thing. Second thing is that there are two types of signals. One is what's called the quadrupole moment type. And the second is memory signal. So this is a sort of a very rough classification. So you have seen expressions where you have this binary and you find out the change in quadrupole moment. That gives you your H mu nu. So that is actually correct if you have slow sources, non-Newtonian sources, in the sense that non-relativistic sources. Whereas if you have relativistic sources, okay, so you have signals which look like the chirp signal which you see in LIGO. Okay, actually it rises, sorry. The frequency becomes large and the amplitude becomes large when they merge, and then it dies off. So this is where you have these black holes spinning around each other, but they are moving at speeds less than c. Okay. On the other hand, you can have some cases where you have a, let's say, you have a black hole in the center of a galaxy, and these stars are going at in a hyperbolic orbit around it. Okay. These stars reach speeds close to c observationally. Okay, they are some fraction of c. Okay. So here you have relativistic sources. When you have this kind of thing, okay, then you don't, this quadrupole approximation is not a correct approximation. You have to solve it in a different way, okay, for the relativistic case. And for this relativistic signal, what you get is, on top of this, you will have a signal like that. So on top of this oscillation, there is a DC step function, okay, which means that the test masses, this is how the test masses oscillate. When the test masses are oscillating, are there for LIGO or whatever, if you have a signal of this time, unbound trajectory of relativistic sources, then you have a step function type of this h mu nu. And what that tells you is that when there are two, let's say there are two, at the end of one arm of LIGO, there are two mirrors. When a gravitational wave passes, they will oscillate, and at the end, they will not come back to their earlier position, but they will stay apart, or they will be steady. So there will be a residual strain which will remain even after the gravitational memory signal has passed, which is why this is called a memory signal, because the mirrors or the test particles retain the memory of the wave which has already passed. Okay, it leaves a permanent imprint on the space-time through which it goes through. And this is a signal which is not yet measured, but it is close to the whatever is the sensitivity of LIGO, advanced LIGO. So this is probably the next target signal which will be seen, and this is how it has a lot of interest, because this signal also connects to what's called the soft theorems, and then you can see corrections to this, log frequency corrections. So you can start probing the quantum nature of this. I mean, you derive these things diagrammatically and see whether you have loop diagrams which will give you a sizable correction or not, and so on. So this is related to what's called the soft graviton. Okay, how much time do I have? Okay, that's enough. So what I'm going to do now today is I'll just derive this and this in the standard picture without going to field theory. Okay, and then tomorrow I'll do the field theory of this guy. This guy is okay. This is a novelty here. So you'll see that the soft graviton, the same thing which I derived today, will be much easily you can derive that using the soft graviton theorems. So there is a point into going to field theoretic treatment, because the calculation becomes simple. Okay? And then you can generalize it to make it, putting loops and so on. Okay, so there is, first I must, okay, I'll start with this gauge. Okay, I'll do it here. Okay, so why does graviton have 2 degrees of freedom? Well, we had the de Donder gauge. So we start with, of course, this equation of motion. So we are talking about the standard gravitational wave, the strain right now, okay? Not the quantum field or the classical field. Okay? Now, if you have free field or free space propagation, then the equation is, so supposing there are no sources and it's propagating in space freely, then this is the equation we need to satisfy. Okay? So starting with the de Donder gauge, this is the de Donder gauge which we assumed. I take this h bar. So this is the thing which we assumed. Now I take h bar mu nu, which is okay. Then this is the de Donder gauge. This is the definition of my h bar. So what I do is I take d alpha of h bar and use that gauge condition. So you can see that if I take d alpha of this and use that gauge condition, the right hand those two will cancel and I'll get a 0. So I'll get basically and then using this condition, this is 0. So this is my de Donder gauge in bar notation, okay, for the bar field. So that is what we are solving. The bar field is the field which we will get for a given source T mu nu. Okay. Okay. So here, right away, so either this equation or this equation, these are equivalent. Okay. This one has, there are 4 equations. Okay. Mu going to 1, 0, 1, 2, 3. Okay. So H mu nu is a symmetric tension dimension 4. So it has 10 independent components, the metric. Okay. And there are 4 gauge conditions. So that has 6 degrees of freedom. And in addition, now we have to see that supposing it's propagating in free space, we have this equation. There are further transformations on h mu nu which you can make. So there is a residual gauge still left, staying within the de Donder gauge. Okay. So let me show you. So h bar mu nu goes to under gauge transformation So if you take the h mu nu gauge transformation and write it the same thing for h bar mu nu, then this is the h bar mu nu gauge transformation under the simple the Xi transformation. Okay. Now you take del mu. This will go to I hope this is correct. Yeah. So take that equation and put a del mu, and this is already 0 for from the de Donder gauge. So basically, what you will get is that you can make a gauge transformation where this is 0 and choose. So you call it, this is a harmonic, call it. So the bottom line is that in the de Donder gauge, okay, staying within the de Donder gauge, you make a further gauge transformation such that this is a harmonic function. That means box acting on it is 0. If you choose these type of functions, then you are able to make a gauge transformation where this is 0. So you are not changing anything. So there is a residual gauge if it is a free space. Okay, if this is obeyed. If that is not obeyed, then this box will be proportional to a source, and then that will depend upon the source. Okay. So now we have, so this is 10 minus 4 minus, this is what? 4, right? 2 degrees of freedom. So this is the G mu nu, symmetric matrix. This is de Donder. And this is residual symmetry in if it's a free theory. That means there are no sources. So free graviton. So the graviton has 2 degrees of freedom. Okay. And then I will not spend too much time on this because Gopu Kumar said he'll explain this at length. So I'll just give you the simple that these 2 degrees of freedom are chosen such that h0 mu is 0. So gauge choice. So this is the gauge choice made if you have a free graviton. Okay. So this is what is the Coulomb or the Newtonian potential. But if it's a free space, it's not a virtual graviton, it's a free graviton, you can choose that a gauge where this Newtonian potential is 0. Okay. And so only the special parts of the graviton are propagating, and they are traceless, and then they are transverse. Okay, that's the gauge choice and traceless. So that's the choice of gauge. That, yeah. So the scalar degree of freedom is the what I was calling H00. What, right? So that is no longer there for a propagating graviton because there is no source for that. No, what is the, from the total, you can have 4 degrees of freedom reduced because of redundant gauge. 4 more you have from this. Now you choose those 2 xis accordingly. So these xis are different from the redundant gauge choice of xis. You choose these 2, 4, such that you have imposed these conditions. So these conditions are not like automatic. They are, after choosing a gauge, we want this. Okay. And in this choice of gauge then, you have a graviton which is traceless and it is transverse. Yeah, this is this free part, this choice. This one, free particle. If it is not a free graviton, then you will still have a H00. Okay, so the bottom line is that, and again now this H, because the H traceless, so now H bar Ij is the same as Hij. So then your wave equation becomes just the box of Hij. All right. How much time I have? Okay. All right. So so now I'll talk about GW from sources. Okay. So what we do is, we have this equation. Oh, sorry, let me write what it looks like. So supposing I have a Ij, we'll call it TT, the traceless transverse graviton, which is propagating in Z direction. So this will look as follows. H plus, sorry. It's propagating in the Z direction, so there is no Z component of H. Okay, only X, Y, and XY components are there. Okay. So XX is called plus, XYY is called minus plus because the total is traceless, and this is HXY, which is called cross. And they have a different, so these are the 2 independent polarization modes for the graviton, of a graviton moving in the Z direction. No, so once you have this TT, this is the only choice. Yes. So I am giving you an example. I mean, in general, it will move in N direction. Then this will have a more complicated. I'm talking about a graviton which is propagating in the Z direction. Then it looks like this. Times, of course, let's say cos. And all these things I have taken without saying this C is equal to 1. So I'm dropping from your expressions, you know, all the C squares are missing. But that's my choice of units. Okay. So what we will do is, we start with this. And for different types of sources, slow moving and fast moving, we want to solve for Hij. Okay. Now, first, we don't want the whole Hij, we want the transverse traceless part of Hij. So we have to take a TT projection. Okay. So for a given direction, so first we have to do is, I'll just first define and then tell you what it is doing. Pij n is delta Ij minus Ni Nj. Okay. So this is n is unit vector in direction of propagation of the graviton. Okay. So what happens is that I have a source, I have a observer, so I have a direction fixed. Given the direction, then I have to find out what are the components of my Hij, which are still viable. Okay. So given the direction, then I have to find out the transverse traceless components. So here we have all the components which are possible, but once we fix the direction, then we may have to make a TT projection. Okay. So this has this property that Ni Pij is Nj Pij. So this is a transless. This gives you that transverse projections are removed if you have this Pij operator. Then we want to do it for, yeah. Okay. And we want to do it for a second rank tensor. Okay. So then well, I define something like that. And this is Pik. And with this definition, this also depends upon n. So all these projections will depend upon the direction n. N is your some direction in space, okay, unit vector. Okay. So what we need is the following. We take this and apply this lambda on this. So lambda on left hand side is HITT is basically IJKL. So if I had any tensor and I make this projection, it will give me something which is transverse and traceless to this direction n which is there in the projection. So I apply that operator both sides of this equation. Okay. So my equation that I get is box ij, this is lambda IJKL. So this is the equation we need to solve to find out the H, transverse traceless H, given a source Tij. What? It's not in the momentum, it's just the direction, a unit direction in the, there is no momentum space here. It's just projecting out the component in the direction of the propagation. So then all these things will be in, which are orthogonal to the direction of propagation. So if the direction of propagation was z, all the indices will be xy. There will be no z in there. That's all. Okay. So then to solve this equation, we use the Green's function, and different, the different limits of this Green's function will give you two different things. One will be the quadrupole and solution, the other will be this memory type of solution. Okay. So what we will do is we will solve this using the Green's function. So Green's function is solution of this. Okay. And then knowing the Green's function, we can then solve for any source by integrating over the Green's function. Okay. And the Green's function for your box operator in 4 dimension, that is well known, or you know how to calculate this. This is And you can put a theta function to say that t is greater than this, or not yet. So now we want a solution. Sorry, this was Green's function should have been it has function about t and t prime. So this is coming from the Green's function, and t of okay. Yeah. So the picture is that x prime tells you the source location. If it's a spread out source, you integrate over the source. So you have this x prime. So this is the origin, and this is x, where my observation is taking place. So this is x and t, the place of observation. Okay. And my source is at a smaller, the spread of the source is much smaller than the distance to the observer. Okay. It's a distant source compared to the size. Yeah. What? Thank you. Yeah. So I take this x minus x prime. This is basically r minus where r is okay. And so what now we can do is first we will integrate out the t prime here and replace this t prime by t minus this thing. So I won't write again. And what I'll do is I'll remove this and make it dq, and this will be t minus so t prime got replaced by t minus x prime after doing the t integral. So this was and then what we do is we expand this around this r. So I will write 1 minus x prime. This I will write as 1 by r. Okay. But TKL, this will be, this is a function of so this will be expanded as So do a Taylor expansion of this around this point. Okay. So this Taylor expansion is of this function time variable. So this can be written as 1 plus so you can do, so notice that this is expansion of this T0, okay, this time, okay, and this basically is a, since this acts on this x prime, okay, this is a velocity expansion, okay, so this is actually will give you the higher orders in v square by c square if you write this in terms of the velocities and take the time derivative, okay. So if you write x prime as v times t, then your derivative with respect to t will give you v's, powers of v. So for slow sources, we keep only this term, first term. So keep this for NR sources. That means v by c is, and that is your quadrupole expansion. Okay, so this is the quadrupole. You'll see how why it is quadrupole. And if you want to keep higher and higher orders, those will be octupole and so on. Okay. So I'll just show you what happens with the quadrupole, and then we'll be. So with all these things, okay, my solution is, I'll write the solution somewhere here. So there was 16 pi g, and then there was 1 by 4 pi in the denominator, so that gives you 4g, and then 1 by x minus x prime. I'm just keeping the leading term, which is x, okay, which is r, which was the 1 by x minus x prime in the denominator. And in the numerator, what you have is then you have this projection operator, okay, and then you have d cube x prime pkl x t minus r. So this is the leading term in the t expansion. The okay, so this is my quadrupole expansion, and then what? Within this integration, x prime. Yeah, thank you. Okay, yeah. So now, okay, this is tedious but simple, so I think I'll just skip some steps. So what we do is, what I can show is the following, that my d cube x prime tij x prime t is equal to half of d0 d cube x prime xi xj prime of t00 x prime t. Okay. I'll show you one or two steps, and it's very simple to show that. So basically, you reduce this ij component of the tij. This one, I should have written kl, but it's the same. So I'll have to show this. But what is this guy? This guy is just the quadrupole moment. This is the mass term or density rho, and this is the second moment, which is the quadrupole. So, and this is the second derivative of the quadrupole. So basically what it tells you is that your signal is a second derivative of the quadrupole moment. Okay, that's the answer. Now what we have got up till here, so quickly run. You can look at my notes if you are confused, but I'll just quickly give you the steps why that, how that you can prove that one. So we use D0, 0, which means this is the stress tensor conservation. Okay. And next time I'll tell you that this actually comes from the gauge symmetry. I forgot to show you how, but I'll show you tomorrow. Okay. But assume for the time being that this stress tensor is conserved. Okay. Then D0 T00 is equal to, so mu, take mu equal to 0 and mu 0 to 1 and you'll get this. Okay. And then you apply it here. Take D0 d cube, I'll just write x. So from this step D0 T00 to dk T0, I've used that. Okay. And then what I do is I integrate by parts and throw out the surface term saying that my T00 has a finite boundedness. It is not, it doesn't expand over all the full volume. So then I can shift this dk and what I will get is this is equal to d cube x xi T0j plus xj T0 I. And I've shifted my lower and upper, so I'll just. So to do this, basically we are using the fact that del xk on del xj, and this minus sign goes when I integrate by parts. So now I apply again one more derivative and use the same trick. I will not bore you with that. And you'll see that finally what I get is d0 dq. This is what I wanted to. So this is what appeared in our wave equation as a source, and we find it more convenient to use the moments. Okay? And with that, we have this formula that you know, that is what? Just wait a second. One second. No. Okay, so there is a miscommunication here. So the integrals are over primes. Okay, 10 minutes. Okay, then I'll do the memory next time. So here, all these things are primes. These are all primes. So I am simplifying that prime part, and I'm not writing the prime because these are general expressions. So R is outside this prime integral. dx prime. See, this prime was the extent of the source and R was the distance. So this was, so I'm doing this part. So I'm actually simplifying this part, And I'm not writing primes everywhere, but I should actually, if you are, it's confusing you. So these are all, okay. So that confirms the sort of, okay. All right, so the final expression was that is xt is 2g upon r, because in the final this thing there will be another 2 coming in. Okay, so this is t minus r, this is the retarded time. So this is the, and 2 derivatives. So this is the form that you usually see. The second derivative of your quadrupole moment at the retarded time gives you your signal, HIJ signal. Okay. And I derived it from the first principles, because now what not this time because I've run out of time. I thought this will all be over in an hour, but yeah, I'll leave that now. Because this is a longish calculation, not a longish 1 page, but this is a nice. So what I will do is that I will do this for relativistic sources which give you this memory. And basically this is nothing but the Leinard-Weishart potential that you see for moving sources in electrodynamics applied to gravity. That gives you the same thing as the memory signal. So I'll just derive that. So I'll do it this way. This is the classical way. Then I'll do it the field theory way, which is then shows you that it's very simple to do it. It motivates the field theory language of doing this kind of thing. Okay, so I think I'll stop here. Thank you.
So we have time for some questions. So anybody?
I just want to ask, I mean, is it going too fast, or too much algebra or too less algebra? Do you have any feedback? Bit fast. Okay, if you write it down and go over it, I actually have typed notes. I'll send you. If anybody writes to me, I'll send you my notes. I have LaTeX these things, so you can. Yeah. Yeah, actually, this is a bit much for 1 hour. There's a lot of things.
So I just wanted a clarification. This R is basically the distance of the entire source from us.
Yes. And
so
R prime is just the inside the source. So what I've done is 1 minus x prime, I've written as 1 x. I've dropped the R prime compared to x. Numerator, I have the t. Since there, it's time derivatives are involved, that's a velocity expansion. In the denominator, it's a distant expansion like you do. Multiple. So distant expansion, I've just take 1 by r. And velocity expansions I've kept. If you want octopole moment and so on, you can still keep those things. Yeah, you can speak.
So as you have already written that there's the interaction term, that is kappa times t mu nu h mu nu. So can we do it the perturbation theory as we do in particle physics?
Yes.
This type of interactions.
Yes. You can calculate like J mu, A mu.
Okay.
This is a current and radiating a photon. Then you can try to calculate a Bremsstrahlung, taking some current, classical current.
Okay.
Same thing with the added index is like a binary radiating a graviton.
And can there be higher order terms like maybe h mu nu terms?
Oh, yes. So there will be multiple gravitons.
Yeah.
So you can have higher order terms then.
Okay. I see.
Yeah. So as you say, as he says that it is kappa is root g, which is 1 upon m Planck. So each vertex you put is suppressed by 1 upon m Planck.
Yes.
So
Right.
unless your energy is close to m Planck, those are small.
Negligible.
Negligible.
Okay. Thanks.
Yeah, in the degree of freedom calculation part, you said when there is no source, we have this residual gauge degree that we are taking del box of xi is 0. So in presence of matter or source, why can't we take this box of xi is 0?
Then your box of xi, if you take that, your box of xi will be equal to that right hand side.
Oh, that source term. Okay.
So then, because the wave equation is h mu nu box is 0, then it will be box h mu nu equal to the right hand side. So box h mu nu 0 gives you box xi 0. So it's a harmonic function. But box h mu nu some source will give you a gauge which is box xi mu equal to that source. So it will be a source dependent term, it is not universal. So this is the same type of calculation why photons have 2 degrees of freedom. Yeah.
So can't we use the same prescription directly without using this gauge choice and taking this projection?
Same what?
Like taking this green function and doing all this algebra. Can't we do it directly from that equation, the free space propagation?
That one?
Yeah.
Well, that has, you see, all redundant degrees of freedom. Whereas what you are looking for, that given a source, given an object, what is the actual degrees of freedom of the two polarizations of the graviton which are propagating in that direction. So you have to put the projection operator to get the correct degrees of freedom, because that has a lot of redundant degrees of freedom. So you don't know which one is the spurious ones or which are not.
Okay.
So it's a complication, but it's necessary. That means no way around.
So this calculation is the first term of the expansion, is it?
Yes, so if you want slow moving sources but V by C corrections to that, post-Newtonian, you take higher and higher terms of that Taylor series which I was writing.
So we still have time for further questions.
And in practice, you don't have to go to this octoball, this I. You can calculate the Tij directly and put it there, and this writing in terms of moment of inertia has a historical value. But directly to do the calculation, Tij is the primary object. You put it there and that will d cube x Tij, and that will give you the.
This last step I could not get actually. This
one?
Yes, last step.
Okay, so what you do is,
These two,
I don't know if I have written this correctly.
These two next step. Last line to next step. This
This one to that.
No, this you have
From this to
written
this.
Last line to right side you have written.
No. So there is one. So what I do is I put one more d0, and so that d0 acts on t0, and I use this kind of relation to again write it in terms of t00.
Okay.
And so I'll have two x's, and then I integrate by parts. Then I'll get that. You can just take a picture from my notebook. It's only this much, but you can write it yourself.
So any more questions? So if we don't have any more questions, then let's thank Subhendra again.
Okay, thank you.